So our two targets for today, just first recognizing if we have a binomial model, and then get into the calculations of those binomial probabilities. And like we saw in the Against All Odds episode yesterday, we're going to be using technology to assist us with those calculations. But that being said, it is important that we recognize what the technology is doing for us. So we will look at the equation. Again, it's something that you will be able to understand. It just gets to be a little bit tedious if you are going to try to do it by hand. So let's take a look at our 4 conditions that need to be met in order to verify that we have a binomial model. First off, we said that we have a success or a failure. Okay? That's hinted by that prefix binomial. We have 2 options. Okay? We call them success or failure. Now again, they mentioned this in the video, a success doesn't need to be a positive outcome, right? Yesterday in the video, having sickle cell disease was a success. So it's just whatever we're interested in or whatever we are counting is the success for that scenario. Now this is pretty easy to identify, and we can make pretty much anything into a binomial model. Okay, we talked with our sampling about our questioning. Like even if you were doing like a political question, like are you Republican or Democrat, you need to be aware of like, well, third party or independent candidates, things like that. We said you could kind of skirt around that by asking like, are you Republican or non-Republican? Or Democrat or non-Democrat, so that you have that this or that categorization. And that would be important here if you were asking those types of questions and you wanted to fit this binomial model. Secondly, we need to have a fixed number of observations. So you need to know going into it that I'm going to flip the coin 10 times, or I'm going to survey 30 people. It's not, I'm going to keep flipping until I get ahead, or I'm going to keep asking people until I get 10 yeses. You need to have a fixed number of observations for the binomial model. Third, we need to have independence with all of our observations. And for this, we're pretty much going to rely on our verbal definition of independence, that outcome of one doesn't impact the outcome of another. Okay? Lastly, that probability of success needs to be the same for each observation. And you'll see that these two kind of go hand in hand with one another. Okay? If that probability is not the same, that's because they are not independent. And the same thing, if you have dependent situations, that means the probability is changing. And so if you wanted to, you could really like put these into the same qualification. However, and sometimes it's easier to look at them separately in order to identify if all of these conditions are being met. Okay? And we'll kind of emphasize what these two mean coming up as we work through some examples. All right, so we have 6 example problems where we just need to confirm, yes or no, does it meet this binomial model? So, our first one down at the bottom, we are flipping 20 coins and counting the number of heads. Okay. Well, success or failure, yes, we're told that a success is the number of heads. Condition 2, flipping the coin 20 times. So fixed number of observations, that's good. Independence, yeah, we know that coin flips are independent. Okay? One flip's outcome doesn't impact other outcomes. And lastly, fixed probability, 50% for every flip. So yes, this does satisfy that binomial model. Number 2, picking 5 cards from a standard deck, counting the number of hearts. We will replace each card each time and reshuffle. Now, that replacement and reshuffling doesn't really make much sense for any card games that I know. However, that's important for ensuring the independence here. And picking 5 cards, success is a heart, failure is any other suit. 5 cards, so fixed number of observations. Independence is true. Because you pick a card, it's one of the 13 hearts, so 13 out of 52, that's 1/4 of the deck. You look at it, you put it back in, you reshuffle, your next selection, you still have that 1/4 probability of picking a heart. So yes, they're independent, yes, the probability is consistent, yes, it is binomial. Now, compare that with this next example, picking 5 cards from a deck, counting the number of hearts without reshuffling. Now, independence is the issue. The probability is changing. So this is no longer a binomial model. And number 4, choosing a card from a standard deck until you get a heart. I already mentioned that. Okay? That does not have a fixed number of observations. So that is not satisfying this binomial model. This 5th example kind of shows you how outdated some of these example problems are. Internet Explorer is by far no longer the most popular web browser, but let's go with it. It says, it is estimated that 87% of computer users use Explorer as their default web browser. We choose 50 computer users and ask their default browser. So, success or failure, using Explorer is a success, any other web browser is a failure. 50 observations, because we're asking 50 people. Independence seems to make sense here. This is the kind of thing where just because one person is using Explorer as their browser shouldn't really impact or influence other randomly selected people for this survey and their browser preference. Now, yes, again, we're putting reliance upon that randomization. If that wasn't there, and maybe you're surveying pockets of different people, then you might not have that independence. But it seems to make sense here. Lastly, fixed probability. Yeah, that's a population proportion of 87%, so that's not really changing with each selection. So yes, binomial model seems to work here. Our last example. A university of 10,000 students has 1,000 scholarship students. We choose 8 students and count the number of scholarship students. Now, a success here would be selecting a student on scholarship. Failure would be non-scholarship student. Picking 8 students, so that's good. Independence. When we're starting with our selection, we have 1,000 scholarship students, 10,000 overall students. So this probability of success is 10%. Now, think about like the deck of cards that we just talked about. We're not picking a student and throwing them back into the 10,000 and they have the possibility of being selected again. That doesn't make sense. So with our second selection, let's say our first one we did get a scholarship student. Now we have 999 scholarships left out of 9,999 students. That is slightly less than a 10% chance. If you divide that out, 999 divided by 9,999, we're looking at 0.0999099991. It's very, very close. And over the course of 10,000 students, I mean, we're only picking 8. So at the very worst, if we kept selecting scholarship students, by the end of this, we have, 992 out of 9,992. I mean, we're still going to be pretty much at 10%. Yeah, 0.9927. So we really haven't changed that much. We are going to assume independence here. Okay? Because this sample size is large enough, it's close enough to being independent for us to use this model. Now, if we had changed this and said, what if there's only 100 students and 10 of them are on scholarship, we still have that starting proportion of 10%, but this is a much smaller sample size there. And as we start selecting 8 students, I mean, there's a chance that by the end of this, we're down to only 2 scholarship students left out of 92. Now, that's not going to be good enough for independence. So, there's no perfect number that I can say that, well, above this, we can assume independence, and below this, they're not independent. And I know that this kind of violates things that you've been taught in math classes before. I know those of you who I had in geometry, first week of school, I told you not to assume things in that class. And here I am, almost second semester of your senior year, saying, yeah, in this case, if it's big enough, go ahead and assume independence. But it's apples and oranges here, right? It fits that model close enough, and it allows us to be able to work with this binomial model because it's across such a large sample size. Any questions on that? Okay. So, let's pause on these notes for a moment and go over to that document on Canvas that's called Is It Binomial? It looks like this. There's 10 problems that are the same types of problems that we just looked at. Those of you in the classroom, I do have a paper version of this if you'd rather refer to that. Mm-hmm. Good? Zach? Good? Okay. I'd like us to take 5 or 10 minutes, go through these examples, same kind of thing. Do they fit those 4 qualifications for being a binomial example? Okay. First few are pretty straightforward. By the time you get to the last few, you could have a bit of an argument as to yes or no. So we'll talk about those, but take a few minutes, see what you can do with them. What these answers would be, and if they fit this binomial model. So as I said, the first few, pretty straightforward. Okay? Observe the gender of the next 40 children born in a hospital. X is the number of boys born. You'll find that this last sentence identifies what a success is going to be for your example. So, success would be a boy, failure would be a girl in this case. So, we have that met. Next 40 children, so fixed number of observations. Independence makes sense, right? If this baby is a boy, that has no impact on if this other baby that's being born is a boy or a girl. And fixed probability. We've seen a couple examples that say it's not truly 50%, but good enough for us. Yes, this is a binomial model. Decide you will have children until you have a boy or a maximum of 5 children. X is the number of boys born. We do not know how many children this couple will have. Okay? If that first child is a boy, then apparently they're done. Okay? But if they keep having girl, then girl, then girl, they're going to try again until they have a boy or maximum of 5 children. Okay? We do not have a fixed number of observations. This is not binomial. Number 3, I rolled 10 dice. X is the number of 6s. All right, success is a 6, failure is anything else. Rolling the dice 10 times, so fixed number of observations. Yes, we have independence on dice rolls. Fixed probability of success, 1/6. So yes, this would be binomial. Now, another dice problem in number 4. You're rolling 2 dice and add them. You continue to roll until you get a 7. Okay? Do not have a fixed number of observations, so no. Number 5, it is estimated that 43% of people sleep regularly with a nightlight in their room. I take a sample of 35 people. X is the number of people who sleep regularly with a nightlight. Okay? Success or failure, nightlight or no. 35 people, so fixed number of observations. Independence seems logical here, right? Especially if this is a random sample that's obtained. And it shouldn't impact others. And then that probability, this is a population proportion. So, yes, we could use a binomial to model this scenario. Numbers 6 and 7 kind of play off of each other. In number 6, in a classroom of 15 students, 10 of them wear glasses or contacts. I choose 6 students. X is the number of them wearing glasses or contacts. Now compare that to 7. In an office building, 1,500 workers, 1,000 of them wear glasses. Again, choose 6 workers. X is the number of them wearing glasses or contacts. Same number of observations, same starting proportion of 2/3. However, this is a much larger sample size than what we have in number 6. Okay, that starting proportion 10 out of 15, but as you start selecting students, that probability changes. Okay, by the time you select 6 students, you could be down to 4 students remaining with glasses out of 9 overall students. And 4/9 is 44%. We know that this started at 67%. Okay, that probability has changed. No, this is not a binomial model because they are not independent of each other, and that probability is changing. But number 7, okay, nothing's changed except for the sample size. 1,000 out of 1,500, still 2/3, but now by the end of our 6 selections, this hasn't really changed that much. Again, this could be down to 900, what do we take, 994 out of 1,494. And when you do that, I mean, instead of being 67%, it's 0.6653. So it's still very close. It's a negligible change in the probability, so you can assume independence, and yes, you can use a binomial model there. Again, there's no perfect number that I can say, well, if you go past this, you can assume independence, but if it's smaller than this, you cannot. In general, something in the thousands, yeah, you're probably okay. But something, well, certainly this small, but in the example we talked about before, that was like only 100 people, the small hundreds, that's probably not big enough. Okay, especially if you're choosing like 6 or 10 or so. Okay. Any questions on these two in relation to each other? All right. Our last 3 could really be open for discussion if we wanted. Okay? I'll show you what I think. I might understand as to why you would feel the alternative is true, but let's just talk about it here. Number 8, only 12% of people like pineapple pizza. I've never had it. I like pineapple, I like pizza. Don't think I'd like them together. Okay. But I guess I should try it first. I choose 25 people and give pizza with pineapple. Participants are allowed to take the pineapple off of the pizza if they wish. Oh, I don't like that. X is the number of people who like the pizza. I don't like that sentence right there, that they can take the pineapple off. Because this probability of 12%, that's 12% of people like pineapple pizza. Now they're given the choice to take it off, and you're asking, X is the number of people who like the pizza. Well, is that the people with the pineapple or without? In my opinion, by allowing them to take it off, you're changing the probability, which goes against that fourth condition. So I would say no, because of that, this is not binomial. Otherwise, it would be. Any arguments on that? Questions on that? Okay. Number 9, an ice hockey player scores on 5.5% of his shots. In a particular game, he gets 8 shots on goal. X is the number of goals he scores in the game. Now, in the video yesterday, and even before that, we've talked about like free throws in basketball are thought of as being independent events. And you're shooting from the same distance every time. You're free from defensive pressure. It's a repeatable event. So for that reason, they are thought of as being independent. Now in hockey, I mean, just like other sports too, we see percentages. Every player has a shooting percentage that's either his year-long average or his career average of number of goals based off of number of shots he's taken to get this shooting percentage. Goalies have a save percentage. You've seen this in other sports as well. But unlike the free throws, 2 hockey shots are not always under the same conditions. You could have a long shot from the blue line, you could have like a tap-in rebound, you could have an empty net goal at the end of the game. For that reason, I would say that this number that we're given as our probability, yes, that's a long-term probability. However, that's not really applicable to every single shot. Okay? Each shot is going to have a different probability of being made or not. Okay? So I would say that you have changing probabilities and that this doesn't really fit that binomial model. Okay? Anybody want to argue on that one? Because I definitely understand how you maybe you could safely assume or play into a binomial model. I'm just saying that you're probably going to run into some problems in the interpretation of those calculations. All right, lastly, number 10, when a paperback book is published, the probability it has defects is 0.03%. A sample of 100 books are examined. X is the number of defective books in the sample. I'm kind of interested. What did you guys feel on this, if you got to number 10? Yes, it is binomial. No, it's not. Silence, indifference. I see both sides of this one. Right? If you think about it, maybe I'm just overanalyzing it, but if you were thinking about a book being published, let's say that publisher is printing 100,000 books. If and when a defect happens, it's probably not just some random occurrence. There's a reason as to why it happens. Okay? Something got off track as they were coming through the assembly line and maybe things were misprinted. Okay, or the binding wasn't just right. But when a defect happens, it's probably not just a one-time occurrence. It's probably happening over and over and over again on that assembly line until that problem is fixed. So, for that reason, I'm thinking that you could argue that they aren't independent of one another, because when a defect happens, the defects are kind of compounding on top of each other. So for that reason, I would say no. However, I could also understand yes, because let's use that 100,000 books being published as an example again. You're taking a random sample of 100 across that 100,000. If and when a defect like that would have occurred, yeah, you would expect to get some of those defective books in there, but the problem's resolved, and then you get some regular books as well. So, in the big picture, it might be independent enough. So, I really don't know what the correct answer would be in that case. Probably like a little bit more information before I had to commit to one answer or another there. But anybody have an argument on that one? Didn't think so. All right. Questions? Now, we've just spent a good amount of time just verifying that we are allowed to use the binomial equation. And as I mentioned before class, that in statistics, you'll find this for the rest of the course, like all throughout the second semester, that yeah, just as important as using the equation to get the answer is being able to verify that you are allowed to use the equation. And I know this isn't AP statistics, but in AP stats and on the AP test, they grade you very harshly on that. If you don't justify why you're using this model or these equations, they basically mark the entire problem wrong. Okay? You have to show, you have to verify that it fits the binomial model, or it fits the normal model, or it fits this, so that then you can move forward and use the equations to get the correct answer. Which, in the big picture, does make a lot of sense. Because unlike Algebra 2 or whatever math class, like, we're not sitting here with 30 problems in front of us and just do this, do this, do this. No, this fits in as one of the pieces of this full statistical process of collecting data, formulating hypotheses, analyzing the data, coming to conclusions, and interpreting what those conclusions mean. So, if you're coming to conclusions based off of faulty data because you use the wrong model, then it's totally worthless, all the work that you've done. Yeah. So this might seem like overkill, but it is important to our process. And I just wanted to not reiterate that, but iterate that. All right. Before we go back to the notes, actually, we might not go back to the notes today. I might just go from here. Let's say that we are flipping a coin. Usual general example. We said that is binomial. Let's say that we're going to flip a coin 4 times. And we are interested in the number of heads. So, I told you that I've already made my last tree diagram. Well, I'm going to make one more. I lied. Okay? So, after that first coin flip, we could have heads or tails. Second coin flip, we could have heads, heads, or heads, tails. Or tails, heads, or tails, tails. Third flip, heads, 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 tails. Heads, tails, heads, heads, tails, tails. This going to be a good lesson video. Yeah, must watch. Tails, heads, heads. Tails, heads, tails. Tails, tails, heads. Tails, tails, tails. All right. So far, after 3 flips, we have 1, 2, 3, 4, 5, 6, 7, 8 possibilities. And that was expected, right? 2 to the 3rd power, 2 outcomes, multiplication counting principle, 2 outcomes in each flip. 2 times 2 times 2, 2 to the 3rd. When we flip a coin one more time, 2 to the 4th. We're going to have 16 possible outcomes. Now, give me a couple minutes. We'll be back. Heads, 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 heads. Heads, 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 tails. Heads, heads, tails, heads. Heads, heads, tails, tails. Heads, tails, heads, heads. Heads, tails, heads, tails. Heads, tails, tails, heads. Heads, tails, tails, tails. Tails, heads, heads, heads. Tails, Tails, heads, heads, tails. Tails, heads, tails, heads. Tails, heads, tails, tails. Tails, tails, heads, heads. Tails, tails, heads, tails. Tails, 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 heads. And lastly, tails, 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 tails. I don't like having to make tree diagrams, okay? But I feel that it's important to show you how bad it can be. Because when you see every possibility in front of you, and again, this is only 16 possibilities, right? Let me change this here. 1 flip, 2 flips, 3 flips, 4 flips. It's only 16 possibilities. If I were to flip the coin 5 times, there's 32. 6 times, 64. 128, etc. What if I flip the coin 50 times and I want to know the probability of 30 or more heads? I mean, there has to be a better way, and technology can shortcut this for us. But if I were to just say right now, you type this in, there's your answer, we go on with our lives, there's a big gap there. Okay? Look at what we have right here. Let me push this up. From our flips, we know we could make a probability distribution. We have x and the probability of x. From our 4 flips, we could have 0, 1, 2, 3, or all 4 of those flips be heads. Okay? Right here. Heads, 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 heads. That was all 4 of them. That was one of the 16 possible outcomes. On the other end, right here, there are 0 heads in that. Tails, 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 tails. Again, only one of the 16 possible outcomes. Everything else in between has multiple heads or multiple tails. Well, I guess that's not the right word, but let's start to look at that. Looking at one head. One head in here would be this one, this one, this one, or this one. There are 4 of those 16 outcomes that constitute one head. Similarly, we could do the same thing for 3 heads. Right? 3 heads would mean 1 tail. So this one, this one, this one, and where is it? This one. So again, 4 out of 16. Everything else has 2 heads. 2 heads, 2 tails. 1, 2, 3, 4, 5, 6. 6 out of 16. This is a probability distribution. All 16 possible outcomes are accounted for. These all add up to 1. 16 out of 16. Now from here, this kind of goes back to what we were talking about before break. We could use this to help us answer questions. Okay, I'm flipping a coin 4 times. What's the probability that I get 3 or 4 heads on my flip? Well, I could add these two together. 4 16ths plus 1 16th, 5 16ths. There's my answer. But let's look at what's happening here, right? We have successes and failures. We already know that this does fit the binomial model. So, like this one right here. This example was 1 head and 3 tails. 1 success and 3 failures. So we had our probability of success, 0.5, and we only had 1 of those. But we had 3 failures, which also had a probability of 0.5, but I'm going to represent it as everything else. 1 minus 0.5. Yeah, I know that that equals 0.5, but let's say that this was 0.4. Then this would be how you get 0.6, right? 1 minus 0.4. We had 1 success and 3 failures. So multiplication counting principle, probability of failure times probability of failure times probability of failure, or failure raised to the 3rd power. Success, we just had 1 of them. So let's think of it as being to the 1st power. So you multiply this out, 0.5 times 0.5 times 0.5 times 0.5, really this turns out to be 1/16, which makes sense. This is one of our outcomes for this scenario, where we have 1 head and 3 tails. But there were 4 ways that this happened. Okay? That 1 head, that could have been the very first flip. It could have been the 2nd flip. It could have been the 3rd flip. It could have been the 4th flip. All 4 of those arrangements need to be considered. That's 4 of the 16. So we're multiplying this by 4. And that would give us 4/16, which is our answer. We'll reduce it to 1/4. Now, this right here is the binomial equation. But in more generic terms, let's write it like this. I'm going to start in the middle here. We said that this is the probability of success. We use a P for that. Probability of success raised to the number of successes, which we're going to use R, times the probability of failure, because it's binomial, that's everything else. 1 minus P, raised to the number of failures. Now, N, we haven't seen it appear yet, but N is going to be our total number of trials. And because R was the number of successes, total number of trials minus the number of successes would give us the number of failures. So N minus R as our exponent. Now the last thing here is this coefficient of the binomial. We had 4 there, but that was kind of visualizing. That was with the help of the tree diagram. We don't always want to have to use that tree diagram. And we saw how painful it was just here. And I was the one making it. You were the ones who had to listen to it. Right? Now, what we could interpret this one here, like this slot that we just talked about, is that of these 4 flips, we want one of them to be heads. Of the 4 flips, we're choosing one of them to be head. 4, choose one. It could be the first position, it could be the second, it could be the third, it could be the fourth. The order does not matter. It's a combination. There is our coefficient. A combination of n and r, total number of observations. R is the number of successes. And this equation can be adapted to fit this entire probability distribution. We could do that for every single slot going across the board. And n, at least on this example, is always going to be 4, but r would be 0, r would be 1, r would be 2, r would be 3, r would be 4. And that would allow us to find every one of these probabilities by hand. Now, little side note here. You could also find that combination with something that you looked at in Algebra 2. Do you remember seeing this before? Maybe it was Mr. Bennett, maybe it was Mrs. Hughes. Do you remember what this is? Zach, do you remember?
I remember seeing that.
It starts with a P, and it's a triangle, and it's a famous mathematician. His first name was Blaise. Kind of a cool name. Blaise Pascal. Pascal's triangle. And Pascal's triangle has nothing but ones on the outside. And on the inside, it's the sum of the 2 diagonal numbers. So 1 plus 1 is 2, 1 plus 2 is 3, 3 plus 3 is 6, and so forth. This is the 0th row of Pascal's triangle. The first row, the second row, the third row, the fourth row. We are doing 4 coin flips. 1, 4, 6, 4, 1. 1, 4, 6, 4, 1 up there. Okay? That is not a coincidence. Okay? This Pascal's triangle could be thought of as a combination, a table or a triangle made of nothing but the combinations, okay, of the number of possibilities and the number of successes. This would be another way to get that full row of combinations if you were doing this by hand. When you saw this in Algebra 2, do you remember why you were looking at it? Or why it came up? Probably not, let's be honest. Well, what you were studying at the time was stuff like x plus y squared. Okay? If you were to expand this, please do not say that it's x squared plus y squared. Right? That's a big no-no that should have been out of your system like 5 years ago. But instead, what this is like x plus y times x plus y, and you would use FOIL to expand that. Okay? But you weren't really interested in the second power at that point. You were more interested in what if this is to the 4th power, or the 5th power, or the 6th power. You used Pascal's triangle as the coefficients of these terms in this binomial expansion. These are binomials, 2 terms, x and y. You're expanding them. That exponent was the row of Pascal's triangle. We are doing binomial probabilities. Once again, these are serving as the coefficients for our binomial probabilities. First term, second term. Okay? These exponents are decreasing while these exponents are increasing. It's the same exact algebraic work that you saw back then. Okay? but it's slightly different direction that we're taking. Now, all of that being said, we still want to use technology. Maybe you find this interesting like me, okay? But I admit this isn't everyone's cup of tea. Okay? But to see how all this comes together can be pretty fascinating, I think. All right? But we care about using this to have us answer questions. So let's look at how technology can assist us. So to do that, I want to start with GeoGebra. Okay? So let me switch screens here and get GeoGebra pulled up. That means I need to log off there. Good. Okay, so in GeoGebra, you're going from the probability calculator perspective. Now, this is the normal model that we had been working with when we did z-scores. We don't want the normal model. We want to use this drop-down menu and pick a binomial model. Now, we have n and we have p. N is the number of observations, p is the probability of success. Okay? The default here was 20. Let's change that. We were looking at 4 coin flips, where the probability of success was 0.5. So update that, and here we go. We were interested in one of our 4 flips being heads. So I'm going to change both of these intervals down here to 1. And one's already there. And there we have it. Okay. The probability that one of our 4 flips would be heads is 0.25. Okay. We also have that full probability distribution right here. 0, 1, 2, 3, or all 4. Okay. 1/16, 4/16, 6/16, 4/16, 1/16. Right in front of us. And additionally, we have the probability histogram. And this is perfectly symmetric. And that's true because we have even probabilities. So our first question was, normal model? No, it's binomial. There are times when the binomial model is the normal model. But there are times when it doesn't, or when it's not, but it does resemble the normal model. Okay? But what this allows us to do, in addition to just single items, is that we can add these very easily. Okay, what if I was interested in not one of the 4 heads, but what's the probability that I get 2 or more heads? Well, I could change these, and I'm going to put this as a lower boundary. What's the probability that x is greater than or equal to 2? It's 0.6875. Or on the probability distribution, I've added these together. Okay? We had 6/16 plus 4 is 10, plus 1 is 11. 11/16 is 0.6875. Now, if push came to shove, we could have done that by hand. We already had the probability distribution in front of us. I could have just added those probabilities together to get this answer. But again, I mentioned this before. What if I wasn't flipping the coin 4 times, but 40 times? There's my new model, and I'm interested in the probability of getting 25 or more heads. My probability is 7.69%. Okay? Just these, and here's that probability distribution. Okay, it's adding all of these on the right together. Okay. That takes some time if you're doing it by hand, but it's very quick and easy in GeoGebra. Additionally, GeoGebra is easier than the graphing calculator. You have this to get you a direct answer. You have the distribution. You have the histogram. Okay? Not to mention the mean and the standard deviation of the distribution, which we haven't talked about yet, but we will. They're right there in front of you. On the calculator, this is 3 or 4 different commands to get all of this information. And it's not as intuitive as GeoGebra is. On the calculator, let me flip over for some shared perspective here. Doesn't like me changing presentations. On the calculator, second distribution. And we've used normal PDF, normal CDF, and inverse norm before. Almost to the bottom. On this calculator, they are letters A and B. We have binomial PDF and binomial CDF. PDF stands for probability density function. CDF stands for cumulative density function. Cumulative means you're adding those probabilities together. So when we were interested in 3 or more, that was a CDF. Okay? But for a PDF, we're flipping the coin 4 times. Probability of success was 0.5. Our X value is the number of successes that we want. So if we wanted 1 head, we put 1 in there, 1 of the 4. The older calculators, it's even worse because you have the open parentheses and you have to put them in this order. Okay. Hopefully you have the newer one. If not, use GeoGebra. There's that 0.25 that we had talked about, the 4/16 or the 1/4 probability. Answering that question about if we had, I don't know, up to flipping a coin 40 times, what's the probability we get 10 or fewer heads? Well, that's a cumulative probability because we're adding all of those scenarios together. So we go to binomial CDF. I said we're flipping a coin 40 times. Probability of success is 0.5. The X value on CDF, the calculator automatically starts adding with 0 and goes through where you tell it to stop. So if you want 0 through 10, okay, the probability of having 10 or fewer heads when you're flipping a coin 40 times, the calculator is going to start adding with 0 heads, 1 head, 2 head, 3 heads, all the way up through 10. So our answer is small number, 0.001, okay, less than 1%. However, if we wanted the upper end of that probability distribution, for example, we're interested in the probability of flipping a coin 40 times and we have 25 or more heads. Well, when I go to do CDF on the calculator doesn't want to add 25, 26, 27 all the way up through 30 or 40. Instead, it wants to add 0, 1, 2, 3, and I tell it where to stop with that X value. So what I need to do is instead have the calculator add 0 through 24. It will add those together. And then because I want 25, 26, 27, all the way up to 40, I want the complement of this because everything on that distribution adds up to 1. So now I need to do 1 minus that previous answer. There's that 7.69% probability that we had seen very, very easily and efficiently with GeoGebra. Okay, so, again, if you just walked in here, it kind of seems like I've got some anti-calculator bias, or like I have stock in GeoGebra or something. I don't. Okay? But think about things and again, kind of go against your own intuitive bias. I want you to try to embrace GeoGebra a little bit, okay? Because of its simplicity. All right, we're going to pause here for today. Next time I see you, we're going to be mostly practicing with these sorts of problems. Now, next time I see you, it's not going to be Monday. It's going to be remotely on Wednesday, which isn't ideal for this sort of practice. So, I'm not exactly sure of what our agenda is going to look like in terms of like the Tuesday, Friday. People are going to have some more class time than you, but we'll make sure that we practice this and we get good at this, okay? Any questions right now? Stop sharing this. All right. And you guys are free to sign off and have a good rest of your day. Good 3-day weekend coming up. We'll see you.